welcome to the afternoon session. We're going to have two talks by Esty Kelman.
So I think that we didn't talk about influences, right? Okay. So I will concentrate on the Boolean hypercube z to the n. So the Boolean hypercube looks almost like this. It's really, sorry. I hear myself. It's really hard. It kind of look like this, at least for n equals 3. And you can try to imagine how it looks for larger n's, but I don't know exactly. And we have the Boolean hypercube graph. So every coordinate here is actually associated with an element in the group z to the n. And the function is on the vertices to associate value for every vertex. And it's good to know this graph. So we have edge between two notes the difference in exactly one coordinate. And Boolean function just give two values, or you can think about 0, 1, two colors, -1, 1. So I like to think about it like two coloring of the graph. And then we can see that we have two different kind of edges. There are the influential edges, the more bichromatic edges, and the edges with the same color. So the bichromatic edges called the influential because they influence the value of the function. And now we can define the influence of a bit of one variable. We can look on all the edges in the direction I and see how many edges are influential. And this many edges up to some normalization is exactly the influence of the variable I. And the total influence defined to be the summation of all of them, which is exactly the number of influential edges in the entire cube up to the same normalization. So these notions are important to know. And let's see how we do this in Fourier representation. Okay, so one important function that I want to introduce is the derivative function. This is a partial derivative function. So for every direction I, we can see how much the function changed when we go in this direction. So this is defined to be the function, the value of f on x minus the value of xi, where xi is exactly the same as x, where the ith bit is flipped. This will be minus xi. Xi minus 1. So the function f x is function on -1, 1 to n to -1, 1. No, it's not true. Okay, so I'll change +/-1, 0, 1 whenever I want. So I hope it will not be confused with this. So if f is Boolean, meaning that it's going to +/-1, then the values that we get here is either -1, +1, or 0. So we can see that we get +/-1 when I is influential here and 0 otherwise. So now if we think about the definition of the influence, was a number of influential edges. this will be exactly the probability when fx is not the same as fx with I flipped, with I bit flipped, and become exactly the probability that the derivative function, the partial derivative, is not zero. So now we can write it as the expectation. So whenever it's not zero, it's exactly when it is plus or minus 1. So we can take the square of it. Excuse me? Thank you. Yeah, okay. So now we have the expectation of some function square. So it's very interesting to see how is this function as Fourier, how its Fourier expansion looks like, because now we can use Perceval to have maybe something interesting. What is this quantity? So it's very easy to calculate it. Just have it. So let us do it here. DIF of x. It's too low. This equals to, we can take the expansion here, and we can see that just become the summation of all the characters that as I. Okay, so this makes sense because in the I direction, all the characters that doesn't contain I just do nothing. One thing, and okay, some interesting fact about Fourier representation of Boolean functions. So if f is Boolean, then what we know about the Fourier coefficient square. What do we know about this summation? It's equals 1, right? So now we have a summation of non-negative numbers that sum up to 1. We can think about it as distribution. So we can think about, let's call it the Fourier distribution, which just pick every character or just subset of n, every character or its subset of n with probability the Fourier coefficient square. Okay, so now what is the influence of the ith variable? Just exactly the probability that S contains I. So this just nice fact. And now if we think about the total influence, that's the summation of all the influences. We want to write it as a Fourier representation, or we can sum all the characters that contains I. This just become, we count now every character as its size exactly. So it becomes f, the size of S. So now this is exactly the expected size factor S. And this will be useful sometimes. It becomes to be the expected degree of the function. So the degree of the function, I guess that's mentioned here, it's just the largest Fourier coefficient that's not 0. So the size of its monomial, whatever you think, and this is the expected degree. Now one thing, so everything that we did up to now was for Boolean functions with values plus minus 1, but we can now take the influence to be defined just as its Fourier representation, and can work for every function that goes to R. And also the total influence, just the same, remain the same definition. And this will be useful sometimes when we want to do it with functions that are not exactly Boolean. Think even about the functions after you applied some noise. They're not already Boolean. Let me introduce the first, I guess.
What was the definition in general? I mean, like this sequence of equalities here, which one definition?
So you can think about the definition as just the summation of the influences. I think this makes more sense. Yeah, just think about it like this. But on the
You're defining now the influence for a general real value function.
okay, so for the individual influence, you can think about the definition as the probability that fx is not equal to fx when you flip the bit I for Boolean functions. And then you can think about the generalized definition as just the Fourier representation. And when you sum all of them, so for the total influence, it becomes the same definition. Just sum all of them. Okay, let me introduce the KKL theorem. One of the questions that yeah.
For general functions, is this still a distribution? I mean, the sum of the characteristics.
So it's not necessarily a distribution, but you always can normalize the function with the summation of all the Fourier coefficients.
Okay.
That the summation is 1. Say about it. Okay, so it started with the work with Benoit and Lineal on collective coin flipping, and they found they thought what happened when the total influence is small, how small can be the individual influences, and they found the Tripes function, which has function, let's talk about it. It's the function O of n or n of O. Or you just say or the O function of ends of many bits. So we have many ends, and okay, so this is the most down. There we go. So this function has every for some parameters of how many O's you have here and how many ends, and every individual bit has influence log n over n. The total influence is of course log n.
This is when you choose it so it's balanced. So the function is roughly half-half.
Yeah. Okay. So balanced right. Okay. So this function is interesting. Why? Because it has some total influence, and all the influences are not very small. And they ask the question whether you can have. Okay, so what's the trivial influence that we have? Whenever we have some total influence, it's always the fact that go up. There exists some I with the individual influence is, this is like very trivial, right? Total influence at least n, just because it's summation. So So if you have, for example, total influence log n, then you have individual influence at least log n over n. And the question is asked whether it's possible to have some total influence and all the influence very small, like to have a smaller total influence and all the, let's say that the total influence will be little r of n. Here's the question. If the total influence is little r of log n, sorry, is it possible that all I influence I of f is about, let's say, the total influence over n, that are all small together. And they try to use combinatorial tools to find some function like this, and they didn't find. And then they came Kahn, Kalai, and Lineal, KKL. And they were the first to use the Fourier analysis to solve Boolean functions questions. And they showed that this is actually not possible. So the answer is no. And every function, every balanced Boolean function at least, but they have also a non-trivial result for non-balanced, has at least one individual influence, which is large, not trivially large. So let me state it somewhere. Yeah. Let f be a Boolean function. Let's say it's balanced. Balanced, I just write it. The expectation of f is 0, meaning it's got -1 with some probability. Then exists some I with influence. I is at least some constant times log n over n. And what we'll do today, we'll prove this theorem. So it has some proofs, and some of them are very easy and short. We'll do today the longest one, but it's very interesting and use some interesting techniques. Just before we go to the techniques, let's talk about another version of KKL. So there is always exists some I with influence I is at least 2 minus the total influence. We put here some constants or not. Some constant. So what they actually proved is this version. So let us see for a minute how we can imply the first from the second, because it's very easy. So 1 implies 2, 2 implies first. Or if the total influence is large, let's say larger than log n ever c, then it's trivial, right? Just divide by n and we get. And otherwise, you can see that using 2, at least log n over 2 is 1 over square root n, much larger than what we need. Okay, so we will prove all of this together. Never mind. We'll prove the first one, but just we need this way. There is another interesting theorem. It's called Friedrich-Hunter theorem, but I'll not talk about it now. And bit. Oops. Yeah. So the first proofs for KKLN reduced into theorems, they were the first to use the Fourier analysis and hypercontractivity and things like that. And why I don't see it now? Okay, never mind. I know there are another proofs that use isoperimetric inequalities and stochastic calculus. And oh, okay. I want to show it also. Okay, maybe I'll not have time. Never mind. Okay. Yeah, and they didn't get any instruction for this, so we can definitely do. Okay. Going to walk. Okay, so the main tool that we are going to see today, and we're going to do everything about restrictions, about almost everything, so we'll know how to do it exactly, as restrictions. So Hamed mentioned that to deal with the higher degrees, we can use noise operator that just kills them somehow. So we'll find another way to kill large degrees, large characters. So let's assume that we have some function with many variables, and we just choose a subset of them, like the colorful ones, to be the live variables, and the other ones we are going to assign some values. We are going to fix them. This is the way that we kill them, -1, 1. And then we end up with a function that we are going to denote it fjz, where j is a set of alive variables and z is the fixing of the other variables. This is going from -1, 1 to j, in that just what it means, to r. And the values of the function defines to be the same values as the original function, with the fixing z. So somehow this z just go to some subcube of the function and takes the values there. And so let's see how it looks in your representation.
Did you say that there are proofs that don't use hypercontractivity? Of KKL?
KKL?
Yeah.
So kind of. They use log Sobolev inequality, which is kind of the same, but
You said isoperimetric inequality. Yeah, unless I misheard also. Is there such a proof?
is what?
Isoperimetric inequality.
What was the question?
Is there a proof with like you said there was a slide that you skipped where you said there's some proof with isoperimetric inequality?
Yeah, so there is a proof of. Okay, yeah, there is a proof, yeah.
Using stochastic calculus, does it use hypercontractivity somewhere, or?
He's going to talk about it, I guess. Some point in this.
What is the forget the names? What is the proof with isometric inequality?
How the proof goes?
Say anything about it?
I don't remember.
Let's keep it for later, because I think most of us don't know any of these terms. So
Yeah. Okay. What is
Let's continue.
yeah. Okay. So let's do some questions. Let's have our function. We can do sections also for some general functions. Okay, so let's see what is the Fourier representation of f. Go over all the characters associated with subset of n, the Fourier coefficient, and the character. Now we have our j and z, the restriction. Let's see how the Fourier coefficients of the restricted function, how they looks like. So what is the value of this function? We can use the Fourier expansion of f. So this is exactly the Fourier coefficients of s, the character s of z and y. We can separate the character s on the values of z and y. Okay, if it's not okay, someone so just let me know. So we can z is outside j and y is inside j. And now z is fixed. So this thing become constant. And the character here is now associated with S intersection with J. And we have many of them in this summation. So let's group all of them together. And what are the characters that we're going to have here? They are all the subset of J. Summation over S. S and J. Y. And what we have here. So this quantity becomes the Fourier coefficient. Okay, so now we have the Fourier representation of the restricted function. What can we do with this? So I think that I said that we are going to talk about random restrictions, and up to now we talked about restrictions, not random. So let's randomize them a bit. So we can choose z randomly. So let's say that we fixed j, and now we don't just take specific z, we randomize it over all the options here. So now we get that the function f jz is a random function. And we can ask questions about how it looks like in expectation, for example. So what is the expectation of let's say what is the expectation of the sum Fourier coefficient over z? So you can see that all the Fourier coefficient of f that contribute to the Fourier coefficient t in the restriction, there are those that have some intersection with J, which is exactly T. And they contribute with different signs, and their sign defined by the character that left in S and not in G is Z. So they sometimes will be plus and sometimes minus. And they will cancel in expectation, they will cancel each other, except to one. And the one that will not cancel will be the one that S is exactly T. So then here we have S minus J is the principal character, and the sign doesn't change. This is not useful fact. I think I don't know why you should use it, but the thing that I want to see here is that actually the Fourier coefficient as represented here as a function of Z with the Fourier representation of this function. So if we define, let's say, GT of Z to be the Fourier coefficient in the restriction, we have this expansion. So this is all the S that has intersection exactly T. Just copy it from here. New. And the expectation of the function, as we already know, is just the principal Fourier coefficient. And if we want to know what is the expectation of the Fourier coefficient squared, so now we have easy formula for Seval, right? So this is exactly the summation of all the Fourier coefficients that has intersection with J exactly T. Now let me introduce some new quantity of Boolean functions. Let us talk about the level K weights. So the weight K of the function f, just define it to be the weight of the characters of size K. Think about it as the probability of S equals K, and S chosen from the Fourier distribution. Now we can ask what is the level K weight expectedly for the restriction. So fact.
If you all doesn't mind, can I ask a question? Oh, sorry. F sub S comma Z. That's you put Z on the coordinates index by S. Is that correct? You wrote F S comma Z.
F S comma Z. Sure. J comma Z.
Okay.
J comma Z.
That helps me. Okay, good. That's you plant Z on the coordinates index by J. That's the
Not index by J.
No. No. What is it?
Is it or
J is
not
the line
outside of J?
J is allowed. So Z is
outside J.
He's in J complement.
Yeah. Yeah.
That's one thing. And you wrote. I guess you wrote magnitude of S intersect J. That's just without the absolute, but that's without the magnitude.
The magnitude of S.
Here. The magnitude in the summation of it. It's a couple of times.
You're recognizing it's like J is equal to T, but you have absolute value. So
Oh, okay. Yeah. So this is just sorry mistake. Thank you. Thank you very much for this. Yeah, here it's absolutely, it's like the size. Okay, well, thank you for listening. Okay, let's see what the level K rate of the restricted function. It takes expectation over Z. This is just calculations. The summation over all T of size K. This is by definition. Now we can take, we already know what is the expected character coefficient square. So we can take it here. It's expectation anymore, this is some minority of expectation. This is just a summation of the square, all of S. Okay. Now with the size of this set equals K. Okay. Any questions? Okay. So let's do more randomization. This is bad. So what's left to do random? So we can randomize J. So let's think about. So let's choose every J to be in J. In J with probability mu. We will stay alive probability mu. Two things before we do this. Two important facts. One fact and one example. So if the function is Boolean, every restriction of this will be Boolean. Okay. Just cool. It takes a subcube. And one example that makes sense, I think. Let us do an example. So let's think about the address function. So what is the address function? We have 2 to k plus k variables. Let's think about 0, 1 now, just to confuse it a bit. We have 2 to k variables. Then we have another k variables. And how the function chooses its values. So it looks what values we have here. And it takes the address from here and choose some variable. And now it will be the value of this variable. So this is the address function. And come as example for many things. And if you think about restriction, let's say that we take J to be the first 2 to k many variables, and then we fix some address, then we end up with a function that's called how? This is just a dictatorship, okay? So we can see that every restriction that okay. So what is dictatorship? This is just a function that when fx just equals xi, this is just exactly what you think it is. You have one variable that defines a function. Yeah, defines the value of the function. So just definition. Okay, example, fx equals xi for some i, or it might be sometimes we talk about the negative dictatorship is minus xi, or sometimes they come together. We'll talk more about dictatorships. Okay, but let's for this. Let's go to random J. Unless you have any questions about this. Okay, so what happened when we choose J randomly? So from this process, we get Fj. Okay. we do two steps. Step one is to find J, to choose J. And then step two, we take random Z from the rest of the variables. Now we end up with a function which is randomized by J and Z. This one. Okay. So now even the domain of J is the size of it is randomized. So for example, how many variables are going to stay alive expectedly? So every variable independently is going to be with probability mu stay alive. So we expect to have mu(n). And for every character, we expect exactly the same fraction. So for every S, the expectation of S intersection with J is going to be mu times S. And why is this interesting? Because the contribution of the Fourier coefficient of S is going to contribute exactly the weight and the characters that has some small interception. Here is the characters that has after the random restriction, the contribution to some level will be exactly the size of the intersection of S and J. So you can see now that this is a way to take large Fourier coefficients, and when we do random restriction, we push their weight to low levels. So let's think, for example, of a function let f be homogeneous. Is it function of degree D? Homogeneous function of degree D is a function that has only non-zero Fourier coefficients only on characters of size D. Another way to say it is that the spectrum of F, think about epsilon equals 0 here, just contain only IS or S equals so if we think about such a function and we want to take all the D weight, the level on the level D weight to very low degrees, it will be useful to use mu to be 1 over D. So if mu equals 1 over D, for example, then for every S, we expect and J exactly 1. And more than that, the probability that S and J, the intersection of S and J equals 1, some calculation, 1 minus 1 over D to D minus 1. This is approximately 1. I meant some constant, far from 0. And now, let's see what exactly I want to say about it. Now, if we actually care about the level 1 restricted functions over J and Z, all the weight is going to go to the level 1, at least a huge fraction of it going to go to level 1 with high probability. So we are going to have here beta of 1. Let's say for these specific functions. And we can relax a little bit the requirement of f to be exactly homogeneous of degree d. Let's think of f such that the term of f has characters of size approximately d. Let's say that there are at least d half and at most 2d. Also here we still have that the probability is very large. And now again, the Fourier coefficients are going to contribute to the level 1. And we can even let the function to have some weight outside of these levels. And if we have just at least constant weight on the levels between d half and 2d, then when we restrict the function and look at the level 1, we'll have at least constant weight there. And we are going to use this kind of functions. And I'll just say why it is sometimes useful to think about functions like this, why it makes sense to think about them. If you think about all the characters, their sizes or ranges between 0 and n. So we can take them, it's called the attic partition. We can partition all the characters to according to the size. Let's say take all the characters such that s is in between n and n half. And then another will be s. Notation. Okay, let me not denote this. And the other partition will be more than that in between n half and n fourths, and so on. So how many parts we are going to end up? We have only log n. So we know that at least one of these partitions is going to have 1 over log n weight, which is not very small. So instead of 1 over log n, we'll think about that we will have constant, but we can deal also with 1 over log n. And I think that we are ready to prove KKL for some assumptions. Yes. So let's assume that our function is of degree d, approximately degree d, which means that the weight on the characters between d half and 2d is at least constant. So now if we want to push the weight to level 1, it makes sense to take mu equals 1 over d. And then we get that the expectation of the first Fourier level is constant. So now we know that there exists at least one j from all the options to j such that the weight is at least constant. So let us fix this specific j. And so now we have that the expectation over z is at least constant. Let us do strong assumptions, but not too strong maybe, and assume that for every z, it's exactly 1. So now what we can know from this, so I'll just remind you that fjz, the restricted function, is Boolean because we started with Boolean function. And when we have a Boolean function that has all of its weight 1, actually this is all of its weight on the first Fourier level, it's actually quite easy to see that it must be a dictatorship. Do I have to convince you, or you're convinced? Okay. Should convince you. Okay, so let's do it a little bit. So what does it mean that the function has all of its Fourier coefficients on all of its Fourier rate on the degree 1? It means that it looks something like this. So f of x, function I, fi, I. Okay. Now think about that you have two is enough, that are not 0, at least 2. So let's say without loss of generality that the first one and the second one are not 0. So it equals to summation I to f1 this 1 plus f2 plus something, 1, 3, and so on. So now let's fix, we know to do restrictions, right? Let's fix all the variables from 3 to n. So we have here some fixed value, call it C. And let's take the four different values of f. So we can put an x1 and x2 plus 1 minus 1, and we can take, I'll start to do it and hopefully I can stop in the middle. So one of the values will be the first one plus the second one plus C. And the second will be, you can put here minus f2 plus C. And we have another 2 values here. And we are going to end up with 3 different values, at least 3, I think even 4 different values of the function, but we have only 2 values of the function. It's Boolean, so it cannot happen. We have only one, at most one Fourier coefficient that is not 0, and if it's not 0, it must be 1, and if it's 1, it must be that fx equals to xi. Either xi or minus xi, because the Fourier coefficient might be minus 1. Okay, so now you're convinced with this fact. So we can think about all the restrictions as, if we let this assumption to be, so all the restrictions are dictatorships. So for every z, we have some j, some xj, small j, that is the dictatorship associated with fjz. Now, coming back to our Boolean cube. So we have this association, and we can do a partition of all the z's according to what j they pick to be their dictatorship. So we have some group that have xj and xk and xl. And now we want to know what is the size of this of these groups, how large aj is. And so I'm going to claim that this is exactly the inference. So let's see why it is true. So you can see that for every z in aj, xj must be influential, because when you put z, then xj defines the, when you fix z, xj defines the function, and we change the function if we change it. And for every other group, AL, for example, xj must be not influential because here XL is the influential variable and we have dictatorship, so we have only one influential variable. So this is exactly the influence. And what we wanted to prove, that the influence is at least log n over n. So if we have some influence which is large, then we are done. We have the KKL. So let us assume that all of them are small. Okay, this is not proof of here. But so if we assume that all of them are small, then we have something to prove. And what we have to prove, so if you remember how we derived the first version from the second, we showed that if the influence is small, then it must be at least one individual influence which is large. So now we'll do the opposite. If the influences are all small, then we are going to show that the total influence is large. So how can we show that the total influence is large? We have to find the influential edges in the cube, where they hide here. So we talked about the edges inside the partition, inside the subsets AJ, AL. So we left now with the edges in between. And so we can see that every edge in between is influential. Why it's influential? Because it's going from xj, the dictatorship xj, to dictatorship xl. So actually, it's not all the edges. Half of them are going to be influential whenever xj and xl have different value. It's hard to see it. Okay. So let us count how many edges we have in between. Luckily, we have edges of isoperimetric inequality that say that if we have a small set, very few in the Boolean cube, then we have many edges going outside of it.
So you said that half the edges that cross between different dictatorships.
Yeah.
Why?
So you should think about it that they are going from one dictatorship to another dictatorship. So whenever these two variables that are the dictatorship are different, it's going to be influential.
Right, but it's possible for these to be like arranged in such a manner. Right. Is there some reason that you expect half of the edges to be?
I'll talk to you in like 2 minutes. Let me just finish the proof, okay? So actually, we are done once we have many edges going outside from each of these small sets. So you can see that this is the edge boundary. It depends on the size of the actually the size of the density of the set. So as the density is smaller, we have more edges going outside. I'll not convince you now about this, but we can do it in the next hour. Just if we sum up now all the edges in between. So we actually sum, if you remember, we thought that the density of these groups is small. It's at most 1 over square root n. So it means that we have at least the number of nodes in each group times log n edges going outside. Summing all of them together, we get many sensitive edges, 2n times log n. We do the normalization of the influence, and we get that the total influence is at least log n, which is exactly what we wanted to say. Okay, if it's at least log n, then we have trivially large influence. So we proved the KKL is a long direction and not for all the cases, but I hope it was interesting. So I guess I will take questions offline or in the next hour or whatever.
guess, yeah, we take questions offline and we do it in half an hour and for the rest of the day.